which will spin a half, but didn't have an exclusion principle. You could spin a half. Before I talk about that, let's talk about photons. So photons have an exclusion principle. Photons most certainly do not have an exclusion principle. And in fact, classical electromagnetic waves are typically waves in which many quanta photons are all in the same state. That's what makes them classical, that they have a very large amplitude, a very large number of photons all in the same state. And so photons most certainly don't have an exclusion principle. In fact, it's almost the opposite. There's a tendency for them to want to be in the same state, but of course photons don't want anything, but they do tend to congregate in the same state, whereas fermions, the half-spin particles, can't be in the same state. So you might ask, could there be a particle of half-spin which doesn't satisfy the Pauli exclusion principle? Or could there be a particle of integer spin? Photon is an integer spin particle, spin 1, or even spin 0. Could there be one of those which does satisfy the Pauli exclusion principle? And the interesting fact is that they go together. Half integer spin, that doesn't necessarily mean spin 1 half, it could be spin 3 halves, spin 5 halves, spin 7 halves. Those half spin objects always satisfy the exclusion principle, and the spin integer particles never satisfy the exclusion principle. That's a theoretical. It can be derived from the principles of quantum field theory. We won't get to that. But I'll show you a little demonstration tonight. All you need is a felt to understand some aspects of it. There's some interesting topological aspects of it which we'll try to get to. This is... No, it's not. That's correct. It's not a theorem.
It's also not true in one or two spatial dimensions.
Right. That's true.
It says there is a maximum number of quanta you can put into a given state.
In the bosonic case? Nope. And strong tendency for them to want to be in the same state. Okay. And we'll try to get to that. Alright, this is a tale of two minus signs. Two distinct different minus signs. One having to do with spin and one having to do with what I'll call exchange. But before we talk a little more about the relationship between the half spins and the exclusion principle, let's talk about the Pauli exclusion principle itself, which has a deeper meaning than just saying you can't put two particles into the same state. It's a statement about the nature of wave functions of multi-particle systems. If I have a multi-particle system, and now when I say wave functions, let's for the moment forget the spin, and I'll come back to the spin and tell you what to do about it, but let's forget about spin for a moment, and say that the coordinates of the particles that we're talking about are called X sub I. I does not stand for X, Y, and Z. It stands for particle 1, particle 2, particle 3, and so forth. So X1 represents particle 1, and so forth. And X could be X, Y, or Z. We're going to suppress the three components of position, just call them X, but I represents the particle. And then a basis of state vectors is to give the positions of all of the particles. Let's write x1, x2, x3. Just as for one particle, we can label a complete set of states by just describing the position of the particle. For a system of particles, we can just label all of the positions, and those are an orthonormal family of states, a complete set of states. And just as for one particle, we can define the wave function in a product, whatever the state vector happens to be. This is an abstract state. It's an abstract state of the system of n particles, some number of particles, and the wave function itself is the inner product of the state vector with the specific state vectors for xn. That is called psi of x1 through xn. What do you do with it? You square it. Well, you don't square it. You multiply it by its complex conjugate. And when you multiply it by its complex conjugate, the result is a probability. It's the probability to find the first particle at x1, the second particle at x2, the third particle at x3, and so forth. So this is multi-particle quantum mechanics in a nutshell. Now, let's suppose that what we're talking about is identical particles. In other words, particles of exactly the same species, electrons, or whatever they happen to be. Ignoring spin for the moment, particles which are identical, we have to ask the question, we talked about it last time, we have to ask the question of whether particle 1 at position 1 and particle 2 at position 2 is it the same state or is it a different state than particle 2 at position 1 and particle 1 at position 2? In other words, that's the blue electron at position x1, that's the red electron at position 2. But electrons don't have colors. They're identical, indistinguishable, and so it's an interesting question to ask, should this state be counted as exactly the same as the state with a red electron at x1 and a blue electron at x2. As far as we know from all experiments as well as from all theory, quantum field theory, relativistic quantum mechanics, the rule is that these are the same states. So, for example, let's just take two particles. That tells us, for example, that the state that I would label x1, x2, blue particle at position x1, red particle at position x2 is exactly the same as red particle at position x2, sorry, blue, which one was number 1? Number 1 is blue. Blue particle at x2, red particle at x1. In other words, there is no difference between a state with a two particles are two particles, say it that way. On the other hand, in quantum mechanics, the physics of a state, the physical properties of a state, don't depend on one particular parameter. They don't depend on the overall phase in front of the state vector. In terms of wave functions, the overall phase in front of the wave function never plays into anything that is physically measurable. That's because all probabilities and all expectation values involve psi times psi star. So it's conceivable that really the right relationship is not that x1, x2 is equal to x2, x1, but something a little bit looser than that. x1, x2 is a phase, e to the I5. Some numerical number, which is a pure phase, e to the I5 or something. So a phi is just a fixed number. It's possible that when you interchange two particles, that the wave function should pick up a phase. On the other hand, supposing you do it twice. Supposing you interchange x1 and x2, you say, well, interchange x1 and x2. The wave function should get multiplied by phase e to the I5, and then you do it again. You interchange them again. You get back to the same place. You get back to the same place. You get back to the same state that you started with. In other words, when you interchange twice, you really do have to come back to the same thing. No other possibility. So the general guess would be that e to the I5 is either plus or minus 1. And an operation, when you do it twice, you get 1. But there are two possibilities. There are two sensible possibilities. Well, you might say